Hey everyone, thanks so much for taking time out of your busy schedule and joining us for today's live session, Model Creation, the Simulation Process. We'll be taking an in-depth look at the issues that are obstructing your simulation process. My name is Diana Dietrich. I'm the marketing specialist here at Swoosh Technologies, and I will be your moderator for today. Just a little on Swoosh. We're an award-winning PLM solution provider and partner of Siemens PLM. Our team has been dedicated in providing you the best software solutions, technical support services, and process-based training to help you optimize your design and manufacturing processes. Our commitment to changing the way designers and manufacturers learn and leverage PLM tools has been a major focus for us for over the last 11 years and will continue to be our goal. Joining me today is PLM solution consultant Dan Wimmenmeyer. Just a little on Dan. Dan has been involved in the PLM area for more than 25 years. From working in the fields of automotive, industrial machine design, and medical devices, his firsthand experience has allowed him to witness firsthand what design and manufacturing software solutions can do to improve engineering processes. In addition to his product development background, Dan has extensive experience in shop floor management and execution systems. Also presenting is application engineer Dylan Malik. Dylan's experience in a variety of industries span nearly 2 decades. He's seen the growth and changes of CAD design and understands how the latest technology has really benefited many companies' processes when it comes to sheet metal fabrication, structural design, surfacing, rendering, animation, and simulation. Dylan's goal is to help your business improve productivity throughout all areas of your product's life cycle. Today, we're talking about the simulation process. As models get larger, so does the amount of data calculated. Many analysts and simulation experts are faced with sorting through massive amounts of data, making it difficult for them to retrieve accurate results, but extremely easy to receive inefficient analysis. So, how can your team overcome these challenges? The simulation process is heavily dependent on the condition of CAD data as it forms the basis of your FE model. During today's session, Dan and Dylan will present to you how you can overcome the issues when trying to reuse CAD geometry in order to create models, and how many companies, big or small, have seen ongoing and continued success. If you have any questions, please feel free to add these into the questions box located in your GoToWebinar panel. Dan and Dylan will have your questions answered during the Q&A portion taking place right after the presentation. So I'm going to go ahead and have Dan take it away.
All right, Diana, thank you. So let me take off. Thanks for the introduction, Diana. I appreciate that. And for those on the call with us today, I hope to, and some of us are probably just getting off of lunch, so I want to make sure that, drowsiness doesn't kick in, so I don't want to be part of that, so I'm going to move on along these slides fairly quickly, and Dylan's going to jump in and do a walkthrough of an actual scenario. So what my job here is to I want to give you a brief overview of what FEMAP is, who we are. I mean, what's FEMAP? So I'll give you an overview, and I'm going to talk about some of the capabilities within FEMAP and what it can do for you. And, what do we mean by easy to use and automated tools and things like that? So that's what I want to step over and step through and show you some of these capabilities. So the big thing about FEMAP is it is a graphical program that provides provides the pre and post processing capabilities for your model. It covers a complete simulation cycle from the FE model creation and analysis setup to the post processing, helping you gain an in-depth understanding of design as quickly as possible. Our goal is to really break it down quickly, fast, in the real world. So the creation of a simulation model, why FEMAP offers a great deal of functionality to help build and visualize a model, application of engineering knowledge is still needed, and it's still required to understand these real-world situations. So careful attention is paid to the creation of loads, boundary conditions, and selection of material. FEMAP is completely independent, CAD independent, it's neutral. We work with a lot of different CAD applications, solvers also, and once again, we talked a little bit about the knowledge too. So FEMAP is definitely not like any other CAE program, it's not a replacement for true knowledge. I just want to make that statement. So let me jump into this a little bit more in depth about FEMAP and who uses FEMAP. So FEMAP is really used worldwide by many different companies, and we just have a few up here that cover from aerospace, automotive. I'll flip up another NASCAR kind of slide here to show you. We're bigger, and we're big in other industries too. So we are widely used, widely accepted for pre and post processing solution. And if you remember too, we're also very capable of working with quite a few different solvers. If you already have a solver that you're very comfortable with, great. Plug us in for your pre and post solution. So let me jump into another example here, or just a quote here. The Ford vision has not changed with FEMAP. We aspire to provide the leading cost-effective, high-performance, finite element modeling solution that's easy to learn and use. So let me give you an example of easy to learn and easy to use. So a company of our Spaceworks tools took full advantage of the advanced modeling functionality that FEMAP offers and the design of next-generation plug-and-play satellite structures. A series of elegant but complex FE models were created using FEMAP to quickly gain insight into the structural performance of the spacecraft structure. If a standard design approach had been used to simply just mesh the geometry with tetrahedral or TET elements, the resulting FE model would have been huge, would have contained tens of millions of nodes, and would have been way too large to solve. Using a hybrid hexahedral method, or hex meshing, and plate element approach, a more manageable model comprising just over 800,000 nodes was created and proved to have very good correlation with experimental results. So you see some of the power of FEMAP, what we can do with inside the tools of FEMAP, which I have yet to show you. But these are some of the models and situations that we're being impressed with within FEMAP. So very real world stuff, out of this world stuff in the case with Spaceworks. So what we're going to cover is we're covering these areas of pre-processing where FEMAP can help you create an accurate FE model as efficiently and as speedily as possible, overcoming traditional obstacles that analysts face every day with the use of existing CAD data. I mean, idealizing that CAD geometry to create an accurate FE model is so critical, and the process of meshing that model. So once the CAD model has been imported into the simulation environment, there are various challenges that we have to overcome still. In general, the CAD model contains much more information than is required to create a simulation model. With it includes details like fillets, chamfers, holes that may be just too small and be really of any significance. If left in the model, they will lead to the creation of small elements that try to capture the small detail, giving rise to just overly large FE models. The CAD model may also contain problematic geometry that can really impede our process trying to create the FE model. Such items are, those who are familiar with FEA work, is the sliver surfaces drive us crazy, right? Short curves, etc. Things like that will misguide the solver, or when we're trying to mesh. If left unhealed, an unhealed condition we call it, it can lead to a creation of badly shaped elements. FEMAP has tools that will automatically, or you can manually select, defeature the model without oversimplifying the model data, which loses vital modeling information. Regarding bad geometry, the FEMAP meshing toolbox includes tools that can locate and remove bad geometry quickly and easily, which is very critical when you're trying to prep your model. So FEMAP is, as I said earlier, is CAD neutral. This is very important in dealing with a lot of different systems out there today. We don't have a single client. It's really standardized on one solution of design. They may have more products of CAD in one or another, but we don't care. We're what we call CAD agnostic. So We stay up to date with the latest CAD applications out there, so that's not going to be a hindrance to moving forward. Really, your selection of CAD is your selection of CAD. We are involved with FEA, and that's what we're solely focused on. So that another example here is NOSIM is a company that was a truly multi-CAD environment, and they wanted to try to standardize with their CAD systems on a simulation and a CAE package that works with all their multi-CAD solutions. So they standardized on FEMAP. As a result, they were able to leave their current engineering process, design process in place, and add to their CAE capabilities with a product that was just no interference at all, which was FEMAP. So let's talk a little more about fixing geometry. So I talked earlier about locating some slivers and curves and things like that. These are troublesome things that we all have to deal with when solving. So short edges, gaps, one of the main challenges has to be overcome is the creation of a finite element model. Sliver surfaces lead to badly shaped elements, as I said before, and finding them really becomes problematic. Just seeing where they reside can be a major task. This is where FEMAP's locating in the meshing toolbox comes into play. It's a dialogue that you can use to control the search parameters and locate all the troublesome curves and surfaces quickly and easily. Having located the problematic geometry entities, there are a number of tools available in FEMAP to make the corrections and allow accurate, well-shaped meshes to be created. So this is just so critical to find these and really get control over these problem areas. The extent of the geometry changes is controlled overall by the user-defined tolerances that you can set in place. So next we're going to cover the typical challenges that arise when trying to create a more efficient and accurate FE model. There are certain approaches in finite element modeling that adopt different modeling topologies to improve the efficiency of model by reducing the model size. These allow you to create smaller FE models without compromising the accuracy of the model. Solid element meshes cannot realistically be employed to represent certain modeling topologies, such as a thin wall or frame type structures. The resulting models would be unmanageable. So it's required that a departure from 3D to 2D, or really 1D, or even zero finite element types through model idealization. Reliance on solid elements to represent design models can lead to a generation of very large inefficient models that take a long time to run, and really many may be unsolvable. So for example, on the midpoint extraction, this is a powerful tool designed to deal with thin-walled models. Such geometries are difficult to model accurately using solid elements without creating huge unmanageable simulation models, and really lend themselves to being modeled using 2D shell elements. Midpoint extraction does just that. The midplane of the solid walls are extracted and meshed using shell elements, thereby creating smaller yet more accurate models of the structure. There are also options to hide exterior surfaces which greatly enhance the visualization and greatly facilitate working with surfaces that are interior to the solid. FEMAP will also automatically offset the thicknesses from the original geometry to elements meshed on those surfaces, ensuring that FE model matches the original geometry model that was intended to be used for the study. To aid with mid-surface extraction, FEMAP includes tools to help connect the disconnected geometry entities by extending a surface to meet the other surface. This can be achieved on surface at one at a time, or when there are multiple surfaces like those that run a square component. All the edges will be located automatically extended to meet the back surface in a single command. So with FEMAP, one has the ability to work directly and interactively with geometry entities on the screen. You can pick points to be moved. You can click on 2 points on the surfaces connected with the points would join together. When the surfaces are joined in this way, they will become automatically connected to form a single body. Using these techniques, it's possible to move entire entities or remove a particular aspect of an entity that extend the width of a, say for example for a slot, or remove it completely by deleting the edge. The direct and interactive nature of these tools makes the task of geometry editing much faster and much easier. Another important modeling capability for consideration with geometry idealization is beam modeling. Many of us do beam modeling. FEMAP offers a method of automatically determining the physical properties of the cross-section that you define, as well as offering a library of commonly used cross-section shapes. Also, full beam visualization available, which lets you view the beam elements as if they were solid, making it easier to check the beam orientation and offsets. Post-analysis, it's also possible to view beam shear force, bending moment diagrams, as well as output contour plots on the beam cross-sections. So now I'm going to turn it over to Dylan, and we're going to see a demonstration of some of FEMAP's geometry idealization of the meshing tools, and we'll set up a boundary conditions and analysis parameters. We'll also see some of the FEMAP's visualization tools along the way.
All right, thank you, Dan. The first thing we're going to take a look at is geometry idealization and the creation of midsurface geometry. And we're going to actually look at the meshing of all these types of bodies. So we're importing varying types of CAD data, whether from part or assemblies. This will be the first thing you'll typically want to do. The role of FEMAP is usually the first time you bring in fairly complex assemblies are the solids and idealizing them into thin shell surfaces or beams, or you can actually leave them as solids. It's not that you can't quickly do meshes on solids. The problem is when you need to mesh a large assembly with complex surfaces, the model size will get huge. If you mesh everything as a solid at one time. I do want to show you that if you want to mesh as a solid, you can just do that and throw a quick tet mesh on there, and it almost happens instantaneously. You can see the quality of the elements, really nice. So you can see we can quickly tet mesh the single model if we wanted to, but imagine we have 100 of these or even larger assemblies. This part by itself is over 100,000 nodes. So the model would quickly get to the point where you couldn't even solve it. So what we do a lot of excuse me. So what we do a lot of times is idealize the geometry down to mid-surface representation. But you do want to capture all these mid-surface changes to accurately represent the stiffness of the part. Because if we have varying thicknesses, we're going to have to show that. So we're going to walk through that step. The first thing to do is go to Geometry, Mid-Surface, Automatic Command. So if you do this a lot, you could easily just make a button on the side so you can get to it all the time instead of going through all the menus. So what we're going to do is tell it to select all bodies. And this command does ask you for a target thickness. So the best thing to do is grab and measure the thickest edge. We're going to use the new Smart Snap and go from the bottom point to the top point. And if you double click the second point, it automatically enters and okays that selection box. It automatically comes up with the thickness. I believe it's 0.255. All right, to visualize it better and help you see what we're doing inside here, we're going to use a splitting tool. So what we want to do is accommodate the various part thicknesses using the split tool on these surfaces. We have a command of the geometry editor, so we're going to just hide all the, and so we can just see nothing but the surface bodies and the wireframe. Makes it a lot easier to see what we're working with here. All right, so we have a command under geometry editing, and that's where we're going to do all our geometry splitting for meshing. And we got one called project curve. What this is going to do is a basic imprint. And if you do that change, if you don't want to change the default setting, you'll see what we're going to do is split the surface with the curves. But it doesn't actually extend. So let's do that first. All right, so just a matter of picking a face and picking an edge, and it's going to project that onto the surface. And you can see what it does. It does not go all the way across. So we do have a command with the option called imprint, extend, and clean. All right, so what this does, even though the curve isn't long enough, it will still see that surface and automatically extend the split to the far edge. All right, so this is make sure there's no hanging edges or any open faces areas. So now that these areas are defined, we can allow for the different part thicknesses. and all the different surface changes. It's pretty much the same thing all the way down. Pick the surface, then the curve. You can be really detailed and try to get all the little blend radiuses and fill it. But for a rough idealization, that's really not needed. Same thing on the back side. We're going to go ahead and grab all these surfaces and split them. At this point, we have all our mid-surfaces selected and split. We can now hide all the original solids, and we can get rid of it and just look at our mid-surfaces by themselves. All right, so what we're going to do now is get rid of all the holes on the side edge, because what that's going to do is just add a lot of extra mesh to the surface that we don't need, especially for stiffness type analysis. So what we're going to do is just go down, and what it's going to do is actually put a point node on there, and you notice it still puts a little dot, so it's actually a point or a reference point for us to actually constrain or use as a mesh. For multiple surfaces, we can Control-Shift and do a polygon selection. So we're going to go ahead and do that on the back side. That's the easiest tool to use, so Control-Shift again, and just window around the hole. All right. Now geometry is now set up. The mesh points are in, and now we just have to mesh the model. So let's set up the sizing. Let's use a common number here. Let's go 0.15 on the meshing size. All right, let's mesh the surfaces. And again, the mesh icon can be set on its own button, so you don't have to go through the menu. But we'll just use the menu command for now. For now, here's the thing we can do is you'll have the varying thickness of the part. You can actually go through and assign separate properties to them. And there is some automated tools to do that, but we have some nice functionality to create a default property, and we'll use just the original thickness so that we selected earlier, the 0.225 on the thickness edge. And we're going to assign a material to it as well. So now let's go ahead and mesh. All right, so we got a pretty nice mesh on the part, and those points are captured. All right. So what we're going to do now is we're going to use a shortcut. It was created in an API to help define and select mesh points. It's handy to have them as a separate for picking later. So let's going to run that API right now. So it's in the grouping command. So now that you see they have all those points highlighted instead of having to go through and try to find and select those. And what we're going to do is actually define those as a floating point node and use those as a constraint. But we have a couple at the top there, so we're going to go ahead and get rid of those. So let's show those again. So what we're going to actually use here is the API grouping. It's just a fast way to actually grab all those nodes in one shot. As I go down the drop down, now you notice there's the API, and if I hit more, you'll see all those points, and then when I select it, you'll see them actually place them as a constraint on the surface. And again, we don't need the two on the top, we just need the bottom ones to be fixed. All right, so now we have this fully constrained, so go ahead and fix it. We're good to go. Now you can see all the constraints at the bottom. All right, so now everything is a uniform thickness. So let's turn the thickness on so you can actually see we have the 225. And we're going to run, the update command. So this is what I was talking about a while ago. Instead of having a properties, we're going to run the update. You can see what it does. It's just the thickness across the offset. So you can see as all the elements now have their own specific thickness changes. All right, let's turn off all the geometry so that we're in more of a finite element scenario. So that's the solid body. Let's turn that back off. So now we have the mid surfaces off, the geometry off, and the mesh. Now let's run an actual simulation. All right, so as you can see, we're going to have a multitude of different studies that we can do. Buckling, heat transfer, nonlinear, linear type of analysis. We're just going to do a modal on this one. So if there's only a single boundary inside of the study, FEMAP will actually go ahead and just run that automatically for you. so it automatically adds 10 in the node. So here's the actual bulk Nastran data. If you want to send it to Nastran, or going to export it to send it to whatever solver that you want, Abacus or any other ones in the list. So now that we have our, it's running, that was very fast to run. So now we have our analysis. Let's expand that out, look at the study. Again, we did the modal, so we're just going to go ahead and just go through the list here and look at the actual animation of the geometry. So you can get a good representation. You can see that some of the thinner sections are a little more flexible. And FEMAP is very accurately capturing the stiffness of whatever solid part or showing the final result on a thin surface mesh. So that's all I have. So let me turn it back to you, Dan.
All righty, thank you, Dylan. Yeah, you covered a lot there with that. So we moved kind of quickly there, but we just wanted to, there's a lot to show, so hope you guys kept with it, and if not, we can definitely answer questions at the end. So what I want to cover now is a little bit more about the quality side, about the model and the checks. So as you saw, the meshing has a direct impact on the final results of the accuracy as well as the efficiency of the solution. In the creation of the FE model of its mesh, it's important to create a mesh with well-shaped elements, as Dylan showed you. The more distorted the element, the more inaccurate your results will be. Model checkout, therefore, is really important. A lot of time can be saved if errors in the mesh are found before the analysis is submitted. FEMAP helps with these issues with a powerful meshing capability through the interactive meshing toolbox, which you saw. Besides numerous tools to help place well-shaped elements around the typical stress, I'll call them stress risers in the model, you can also apply a number of quality checks prior to the analysis submission. This just all streamlines the simulation process and keeps it moving efficiently. So the tools available in FEMAP's meshing toolbox help you really interactively modify geometry prior to that mesh creation. Geometry splitters, which can be used to split large surfaces into smaller ones to help align geometry and create surfaces that can be map meshed, what we're saying, which is a means by which regular quadrahedral surface elements are created. Offset curves, which can create map meshable regions around complex geometry that compromises multiple curves, and not finally, but washers, which use offset curves to create map meshable regions around holes, which are the typical stress razors, which is where you would usually want a very good regular mesh for accuracy. And finally, pads, which breaks the surface geometry surrounding the hole into four map meshable regions. The purpose of these tools, of course, is to ensure that the mesh is accurate and can be replaced easily around stress risers or stress razors in the model. So we have those in the toolbox. You also have full control over the meshing parameters on the underlying geometry within the meshing toolbox, as well as setting the number of elements on the edge of the surface or curves. You will also have further operations to select map meshing, which ensures even distribution of well-shaped elements over those surfaces that you choose. So for very detailed mesh adjustments, you can even manually move individual nodes around the underlying surface geometry. This becomes really critical at times. FEMAP ensures that they adhere to the underlying surface of the curve, which can be this can be a useful tool to improve the element shape, that it can be past the your selective element quality for the criteria that you've chosen for your mesh. An important aspect of the pre-processing simulation model before submitting it for analysis is part of the checkout, right? So if we don't do some of these things ahead of time, it's just gonna the whole workflow will get longer and longer. Element distortions and other element quality checks are included in FEMAP's meshing toolbox, can be shown interactively during the meshing process. A good quality mesh in areas of high stress gradient is important for accuracy. Other checks available on FEMAP allow you to verify that there are no discontinuities in the model by viewing free edges and faces, something that cannot be checked by just looking at a model. Check coincidence elements and nodes, which can also be indicators of discontinuities, load checking by summing forces, and finally mass property checking. A powerful method of simulating complex loading within FEMAP's pre-processing functionalities are the data surfaces, useful to define more complex loading conditions. Data surfaces come in various topologies from 1 to 3-dimensional as well as some special cases. Another example shows how temperature distribution can be oriented to apply to a component for further analysis. With the import of an assembly model, FEMAP offers the ability to automatically determine contact between the assembly components and beyond that to easily define the nature of the contact, whether it be linear or nonlinear, with or without friction, or glued. Also importantly, with assembly modeling is the ability to view components easily. FEMAP includes some helpful features such as transparency to help see internal components. Besides contact and gluing, FEMAP offers other methods of connecting components of an assembly together, including weld, spot weld, and fastener elements, bolted connections, which can be preloaded. So no matter how the assembly connects together, there is a suitable option available within FEMAP to ensure the correct interaction and hence correct load transfers between assembly components. It's rare that a structural integrity of a component can be investigated in isolation. So the ability to model an assembly accurately representing component interaction is important to the model. With the ever-increasing use of composites in materials manufacturing, the need for good analysis tools within the design of composite materials is becoming more and more important. FEMAP has various capabilities to help you quickly view and understand the existing model or create up a new layup from scratch. A big challenge with modeling composite materials is visualizing the model in layups. FEMAP's grouping functionality can help here, as you can define groups by layup, which makes visualization easier. The layup can be viewed diagrammatically with the layup viewer. Using the layup editor, the laminate definitions can be created and edited very easily inside the toolbox. With the idealization of composite structures, apply discontinuities due to drop-off, create situations in finite element models where adjacent elements contain differing numbers of piles. Results interpretations of component structures can therefore be laboriously tasked requiring manual identification of corresponding ply results from elements to elements across the structure. The FEMAP global ply capability addressing this problem by allowing you to identify global piles and use them to visualize results on continuous piles across the structure. So FEMAP has a lot of powerful modeling and visualization capabilities and functionality, all accessible with an easy-to-use, intuitive interface, which brings many benefits, including increased productivity and reduced learning curve and training overhead. In the pre-processing stage, FEMAP offers the ability to import geometry from just about any source and has the functionality to efficiently convert CAD data geometry into a simulation model. A key part of this is the meshing process, which is made easier with FEMAP's high-performance meshing tools. In the post-processing stage, FEMAP offers a wealth of viewing functionality to help engineers interpret the simulation results and better understand the model behavior. Essentially, FEMAP sets a new standard in open simulation by bringing both CAD independence, where CAD data can be accessed from just about any source, and solver neutral, and that FEMAP can create simulation models for all the major commercial solvers. At this point, I'm going to turn it over back to Diana for Q&A.
All right, so I know we went a little bit over time, guys, but I just wanted to make sure that we did answer a few questions that are in the queue. And just keep in mind that if you do have any questions that you further want to put into our box, please feel free to do so. Every single question that is asked will be asked anonymously. And also, if we don't get to your question today, I'll make sure that Dan and Dylan do have your contact, or will get back to you by phone or by email in the next few days. So Dan, Dylan, the first question that we have in our Q&A in our questions box is, you stated that FEMAP is CAD neutral. We're using Creo. When importing geometry from my CAD file, then will it still work?
I don't think there's an actual specific Creo import, but I know Creo Pro E, they can easily outport to an IGES or a set file, and that's really all that you would need to bring it in. So it'll bring in all IGES, step, parasolid, those types of geometries, no problem.
So another question that we have in our queue is, does Nastran come with FEMAP?
I can answer that one, Dylan. So, yeah, so Nastran, it depends on the package you buy. We have a basic package that does include our NX Nastran solver. So that's a complete, it's a pre and post, and you get the solver with it. So it just depends on when you talk with us. If you don't have a solver currently in place, absolutely you're going to need one. So NX Nastran is what we sell with Siemens.
And we have time for one final question. What if I noticed I had made an error in my file? How easy is it to turn different elements and geometry on and off?
Oh, and actually, FEMAP is actually pretty slick in that. I didn't show that, but you can actually do some geometry modification in the actual FEMAP software. You can actually take a couple, you can combine simulations. So if you got a part from something else that you simulated, you open up another part in FEMAP. You can actually window or just kind of use coordinate systems to combine geometry, or just portions of geometry. You can kind of window select and grab nodes that you want to use and kind of just get rid of the stuff that you don't. So a lot of that can actually be done inside FEMAP.
Thanks, guys. So unfortunately, we are out of time for today, but we want to make sure that if any questions do arise following the session, that you can reach out to us. But before we end the session, I wanted to make sure you're aware of that if you're interested in trying FEMAP for free, you can do so. So Dan, if you could, thank you. So just go ahead and head on over to sourcepack.com/FEMAP, and then what you'll want to do is click on that image that you see on your screen right now, and you'll be able to get yourself a free 45-day trial of FEMAP. You'll be able to see firsthand how powerful this software is and the potential it offers for your team. So if you do have any questions about FEMAP or you want to learn more about it, please feel free to reach out to me, Dan, or Dylan. Or if you're already in touch with one of our sales reps here, please feel free to reach out to them. Either way, we're all here and we're all more than happy to help in any way we can, so you're one step closer to meeting your production goals. Once again, guys, thanks so much for joining us today. We hope you enjoyed our session. Also, I just wanted to let you know that you will be receiving a replay of the session in the next few days, so please be on the lookout for our replay email, which will also have the FEMAP trial link in there in the case you're ready to start your free trial immediately. Thanks, guys, for joining us. Thanks, Dan. Thanks, Dylan. Bye.
Okay. Thanks. Bye.